Stanford University.
Yeah, all right, so let's just for a moment stop and say what we'll do next time. I'm not sure whether tonight I will get to one of the key puzzles, which is called the gauge hierarchy. We may. I had planned it in my notes, and we may get to it, especially since I'm getting rid of the review. But next quarter, I want to study some of these paradoxes, not paradoxes, but difficulties of the theory, and how things like supersymmetry relate to them, how supersymmetry may or may not solve some of these puzzling features of the theory. How unification, what unification? Right now we have SU3, we have SU2, and we have U1. I'm talking now about the forces weak, electromagnetic, and strong. Do these somehow sit in some bigger structure? Is there a group, for example, which contains the subgroups, SU3, SU2, and U1? I haven't told you what a subgroup is, but you can imagine. Is there a bigger structure, a bigger mathematical structure that contains SU3, SU2, and U1? Yes. There's a subgroup, there's a group called SU5. And there's a lot of interesting evidence that this whole structure that I've described so far fits very, very neatly into an SU5 structure, in which quarks and leptons are all part of the same multiplets. We'll talk about that. Supersymmetry, unification, and the various puzzles that arise. And I will tell you a little bit about what LHC is cooked up to discover. All right, now, one thing that LHC was cooked up originally to discover was, of course, the Higgs boson. The Higgs boson, discovering the Higgs boson is not just discovering the Higgs boson. For example, it's more than just discovering the existence of a particle. It also involves a whole bunch of properties of this particle, which are all related to the fact that it is a Higgs boson. For example, I told you, I think it was last time, how the Higgs boson and the Higgs phenomena is related to the masses of fermions. We looked at the Dirac equation. Instead of looking at the Dirac equation, we might have looked at the Lagrangian for the Dirac equation. I don't know if we ever wrote down the Lagrangian for the Dirac equation. I don't think we did. Let me write it down for you. Yeah, we did the Klein-Gordon. Let me write it down for you. It's very easy. We first write down the Dirac equation. Derivative with respect to x mu of, derivative with respect to time of psi, what was it, minus or plus, I don't remember, plus derivative with respect to x sub I, where x sub I means x, y, or z, times alpha I psi. We can put the alpha I out here. And we set that equal to what? Beta times the mass, right? Times psi. That was the Dirac equation. Let me move everything over to the left-hand side. Did I ever tell you my greatest mathematical discovery? You don't need the equal sign, right? Right. You made that discovery too. How old were you?
No, you told us.
Oh, I told you. Okay. Okay, this is the Dirac equation. Now, supposing I want to derive this Dirac equation by variation with respect to something. In particular, it happens to be psi star that you vary it with respect to. Well, there's a very easy way of constructing a Lagrangian such that when you vary with respect to psi star, it's the Dirac equation which falls out. All you have to do is multiply the Dirac equation by psi star, psi dagger, or psi star. Now it's not zero. It's still zero, but now it is not the Dirac equation. It's the Lagrangian for the Dirac field. All right. What does it have in it? It has terms, psi dagger, derivatives of psi. Those are the kinds of things which move a particle from one point to another. Remember in the Klein-Gordon equation, the kinetic term was associated with the hopping of the particle from one point to another. And that's what these terms are. It absorbs a particle and moves it to a new point of space-time. That's what the derivatives do. They move it to a new point of space-time. At the same time, they jiggle its spin in a certain way. That's what these kinetic things are. And the mass term is just a term which takes a particle, absorbs it, and emits it from a point of space with no derivatives at all. It just absorbs it and emits it from the same spot. That's the Lagrangian for the Dirac equation. And it's, yeah.
Do you need a gamma naught in there after the psi dagger?
No.
Psi bar?
No. No. Okay. All right. So you asked me, I hadn't used that language, but I will now use that language now. Good. Just for those who are curious about the more covariant language, if you take psi dagger and you multiply it by beta, that gives you something that's called psi bar. If you want to get back from psi bar to psi, you multiply by beta. Why? Because beta squared is equal to 1. All right? So you can write this, you can rewrite this in the following way. You write it as psi bar beta, that's just psi dagger, d by dt. And then over here, what will we have? Then we will have plus psi bar beta alpha sub I derivative with respect to x sub I psi. And then what about this one over here? Sorry, let's put the, this one is going to be psi dagger beta m psi. What will that be? No, well, it's just psi bar m psi. M psi bar m plus m psi bar psi. Now, if I change the name of these symbols, we can call beta gamma naught. Why naught? Because it's connected with, naught usually refers to time. The 4 coordinates of space-time are the 0 component for time and 1, 2, 3 for space. So this one's usually called gamma naught. Beta is sometimes called, in fact, most frequently in modern physics, the alpha beta notation is mostly abandoned, and you use gamma. So this becomes psi bar gamma naught dt psi. And this one, now we're going to change the name. Beta times alpha, just the product beta times alpha I, we're going to call gamma I. Psi bar gamma I di psi plus m psi bar psi. That's the Lagrangian. And now it has a very, very neat form. You can think of gamma naught d by dt as being gamma naught d by dx naught. This is gamma I d by dxi. It looks like a nice covariant sort of 4-vector product of gamma matrices times derivatives. In other words, you can write the whole thing in the form psi bar gamma mu d by dx mu, let's just call it d by d mu. Now mu goes from 1 to 4 plus m psi. Okay, that's much more elegant than the original form that Dirac wrote down. These are also, the alphas and betas are called Dirac matrices. The gammas are also called Dirac matrices.
Yeah. You said the psi on the far left here was psi bar, and you didn't bar it.
Right. Psi bar. Right. All right, but all you have to remember, though, is that psi bar is not psi dagger. It's psi dagger with an extra gamma naught. All right, but this is the elegant form for the equation. In fact, psi bar psi happens to be a scalar. And psi bar gamma psi is a 4-vector. It has an index mu. So this is a more elegant way to present the Dirac equation, the Dirac Lagrangian. The Dirac equation is just setting this equal to 0. Okay? The Dirac Lagrangian looks like this. Now, from this point of view, let's just examine, well, let's examine the various terms. You know there's a 5th Dirac matrix. Anybody know what it's called? Gamma 5. What's missing? Gamma 4. There's no gamma 4. In fact, it's just a glitch. There's one more gamma matrix, which is called gamma 5, which happens to be the product of gamma naught, gamma 1, gamma 2, gamma 3. It's called gamma 5. It happens to be one more matrix. And in fact, the eigenvectors of gamma 5 squared is also equal to 1. It has 2 eigenvalues, +1 and -1. And the 2 eigenvectors, or the 2 eigenvalues, correspond to the left-handedness and the right-handedness of the particles. Gamma 5 is called helicity. Chirality, chirality. Handedness. Chiral for hand, you know, like what was the Greek word for hand? Chiron, Kairos, Chiron, something with a chiron, C-H-I-R, chirality. Yeah, gamma 5 is called chirality, and it can be plus or minus 1, and it corresponds to the handedness of the 2 particles. Now, if you work it out, if you work out the various things, you'll find that this term here does not couple the left-handed and the right-handed components of psi. The left-handed and right-handed components of psi mean the things with eigenvalue +1 and -1 for gamma 5. But just think of them as electrons or particles with a right-handed helicity or a left-handed helicity. These 2 here, these 4 here, do not multiply left-handed times right-handed. It just happens they don't. You can work that out from by yourselves. This one does. Psi bar times psi happens to be, happens to be, let's write it this way, happens to be psi dagger left, psi right, plus psi dagger right, psi left. That's what it is. So the mass term here mixes up the left-handed and the right-handed particles. That's what a mass is, a Dirac mass is. It's a term in the Lagrangian. It seems weird that it should have anything to do with inertia. It's a term which causes a left-handed fermion to flip to a right-handed fermion, to flip to a left-handed fermion, and so forth. And that's what's over here. Okay. The other terms don't do that. So that means a massless fermion has a definite chirality. The mass term flips the chirality back and forth and back and forth. Yeah. All right, then we talked about a class of interactions, the weak interactions. Let's put in particular focus on the Z, the emission and absorption of Z bosons. That is purely left-handed. For some odd reason, the Z boson only is emitted by left-handed particles, not by right-handed particles. This is not true of the photon. This is only true of the Z boson. Sorry, the W boson. The Z boson is a little more kinky. It has asymmetric couplings to left-handed and right-handed. But let's focus on the Ws. They couple through only the left-handed degrees of freedom. So that means that in effect, with respect to the charges, with respect to the transformation properties under the SU2 that's connected with the W, the emission of W bosons, the left-handed fermion is charged and the right-handed fermion is uncharged. You're not allowed to put in a Lagrangian something like this, which would take a charged particle to an uncharged particle. It would mean a process in which a charged particle would come in and get absorbed, and an uncharged particle go out, violates charge conservation. So this would not be a legal term in a Lagrangian that had a gauge symmetry which only coupled to left-handed particles. All right, then the question is, how do you get a mass for fermions? We know that electrons and quarks, they all have masses. There's something wrong. Here's where the Higgs boson comes into play. The Higgs boson also plays the role of a charged object with respect to the SU2 of weak interactions. In fact, it's a doublet. Just like the electron and neutrino are doublets, the Higgs boson is also a doublet. I didn't emphasize that, and I'm not going to emphasize it. I've sort of skirted around it. The Higgs boson also transforms under SU2. And roughly speaking, the way to make this into a legitimate interaction is to multiply by the appropriate Higgs boson field here. The Higgs boson, if you like, carries a weak charge, which is either the same or opposite, depending on which component we're talking about, as the weak charge of, let's say, the electron, if we're talking about electrons here. The right-handed particle has no charge with respect to the weak interactions. So what we have to do is put a Higgs boson here and a Higgs dagger here. This means the emission of a Higgs boson and the emission of an anti-Higgs boson, if you like, with the Higgs boson carrying off the charge of the left-handed particle when it became the right-handed particle. So we introduce into the Lagrangian something which takes a left-handed fermion, emits a right-handed fermion, but also allows a Higgs boson to be emitted in such a way that the weak charge of the electron or the quark or whatever it is escapes in the form of the Higgs boson, the Higgs doublet. And that would be the end of the story, except for the spontaneous symmetry breaking, which has to do with the Higgs field getting an expectation value. The Higgs field, well, I think we called it phi last time, didn't we? I think we called it phi. Let's just continue to call it phi. And we emit a phi particle here. That would be the end of the story, except that for whatever reasons, nature has chosen the energetics of the Higgs field, this phi here, to have one of these Mexican hat potential energies. Why did it do that? Why did nature do that? We don't know. Okay, but we're very lucky that it did. Otherwise, chemistry would go to hell, and things would be very, very unpleasant. But with one of these upside-down Mexican hat potentials, that means that phi is equal to a number, just the magnitude of the Higgs field here, which we called F, plus a fluctuation away from that value. And that fluctuation is what we actually call the Higgs field. All right. So let's go back now. What happens to this term? What happens to these terms in the Lagrangian? They break up into two pieces. Not these two pieces, but these two pieces. One of them is, oh, I left out one thing. What did I leave out of this expression? A numerical number, G. The Yukawa coupling, let's call it G sub y. And there's a different G sub y for each fermion. These two should be the same. All right, G sub y is just a number. A pure number carries no dimensions. They're called Yukawa couplings. And where they came from, I don't know. Somebody wiser than me put them into the Lagrangian. Okay, so here they are. All right, now let's use the fact that phi is equal to a non-fluctuating part, which we called F. For the non-fluctuating part, we called it F. And for the fluctuating part, we called it H, the Higgs boson. That's not my notation. That's a standard notation. So this becomes GY F times psi dagger left, psi right, plus psi dagger right, psi left, plus GY Higgs field times the same thing. Same thing. Okay, now we have a prediction for what the number F, where did that come from? The number F we obtained, that same number F went into the mass of the Z and W bosons. The shift of the Higgs field also determined the mass of the Z and W bosons. Once you've measured the mass of the Z and W bosons, and this was done a long time ago, they were measured, the masses are measured, about of order 100 GeV, 90 GeV, something like that. So that told us what F was. That told us what the number F was. F is a number of about really 200 GeV for F. Okay, so that's a number. It has units of mass, incidentally. F has units of mass, 200 GeV. Okay. Once we know that from Z and W physics, then from the masses of the fermions, we can read off what these Yukawa couplings are. Once we know, for example, the electron Yukawa coupling is some very, very small number. Why? Because the electron is much lighter than the Z and W. The Yukawa coupling for the top quark, that's large. Why? Because the top quark is so heavy. So the masses of the quarks wind up being these Yukawa couplings times F. And so far, we've really gotten out no more than we put in. We've gotten out no more than we put in. We got F from the masses of, well, a little bit more, but basically mass, the masses of the ZW system, we got F, and then from the masses of the fermions, we got the Yukawa couplings. All right, so if that's all there was, we would have put in as much as we got out. But now we also have something else. We have GY Higgs times things like, let's just call them psi dagger psi. These are terms in Lagrangian which take a fermion, this could be an electron, it could be a whatever it happens to be, which take a fermion, absorb it, and re-emit it, plus a Higgs boson. So these are then processes where, let's say, electron, or it could be muon, or it could be tau, or it could be some quark, emits a Higgs boson. Or it could be a Higgs boson coming along and decaying into an electron and a positron. Same diagram. Okay. So once the Higgs boson materializes as a particle in the laboratory, we should know what the various decay rates are for it to decay to the different kinds of electron, positron, muon, anti-muon, or whatever. We'll know all of the interactions between the Higgs boson and the fermions and be able to predict all the decay rates, all the Higgs boson decay rates. Obviously, it'll prefer to decay to heavier particles as long as there's enough energy, because these Yukawa couplings are larger. The Yukawa couplings are the coupling constant for the Higgs to break up into its constituents, into its decay products. So at the moment, I mean, Higgsology is a pure theory in the sense that it's predicted by the theory. There seems to be no other way to make it mathematically consistent, but neither the Higgs nor the direct couplings to these particles and so forth have been detected. That will happen. Well, I hope it will happen. And so there's a lot of predictive power. The theory also already has an enormous amount of predictive power in the interactions of the Z's and the W's, which are experimentally detected. The interaction of the Z's and the W's not only with respect to the fermions, but with respect to each other. Z's, yeah.
How would you actually predict the decay time? I don't mean going through all the nitty-gritty details, but I mean, sort of how would you set it up to actually make that prediction?
Well, you calculate a Fineman diagram. You calculate a Fineman diagram. You can just think of it as elementary quantum mechanics. This gives you a term in the Hamiltonian, which takes the Higgs boson to a pair of particles, and it just gives you the transition amplitude, which you square. And once you've squared it, you integrate it or sum it over all the final states. There's an integral to do, and that gives you the decay rate. It's a standard calculation that is basically a Fineman diagram. If you like, this gives you the amplitude. You square the amplitude to get the decay rate. Squaring the amplitude you can just do by putting this right on top of itself like that. Here the amplitude is squared. And that becomes a Fineman diagram. You calculate the Fineman diagram by Feynman's rules, and one of the things that comes out of it is the decay rate. So, this is more than we're going to do here. That's we have to do. So it's a very, very definite calculation within standard quantum field theory. And it's the kind of calculation we've been doing since the 1930s, so it's quite well known. The only things that you have to put in, which are new, are the values of these coupling constants, masses of particles, and so forth. Okay, so that was the masses of fermions, the masses of the Z and W bosons, all of them being proportional to this constant F. Why don't we talk about the Higgs itself? Let's talk about the dynamics of the Higgs boson. The dynamics is really all contained in this Mexican hat potential. The minimum of the Mexican hat potential tells you how much the field is shifted, and it tells you what F is. All right. You can make up different potentials that have this shape. There's a favorite one which actually has some important theoretical significance. And it goes as follows. Let's go to the origin over here. At the origin, the Higgs potential is a sort of upside-down parabola. Let's forget what it does far from the origin. Let's just concentrate on near the origin. An upside-down parabola means something like minus, let's call it mu squared, phi squared. And it's traditional to put a 2 in here. It's just traditional. Minus, because it's an upside-down parabola. Remember, if it was plus mu squared f squared, phi squared, what would you call this term? You would call this term the mass of the Higgs boson. You would call mu the mass of the Higgs boson. Or you would really call mu squared the square of the mass of the Higgs boson. Making it negative is a little bit weird. It's as if there was an imaginary mass for the Higgs boson. But don't worry, there's nothing wrong with this. It's perfectly okay to have a potential which is upside down. The only thing which is unusual about it is putting the field at the origin is not a stable position. It tends to roll off and roll down the hill. Whereas if the mass term was positive, it would oscillate about the top, about the central position here. So the field does not oscillate about the top because of this minus phi squared. Now, If all you had was minus phi squared, it would just go down and down and down, and the field would just run away to infinity. There would be no ground state to the system. There would be no vacuum. Vacuum is the state of lowest energy. There would be no state of lowest energy. So we've got to put in something to keep it from running away to infinity. We better put in something to turn it up. Simplest thing to turn it up is plus lambda, where lambda is just a number, pure number, times phi to the fourth. Why do I want to put in phi? Why not phi cubed or phi to the fifth? Why not odd powers? Because we want to keep it symmetric on both sides. This was an important aspect of this potential, was to keep it nice and symmetric. All right. So phi to the fourth is symmetric, phi cubed is not. This is the next thing you can put in. You can put in all sorts of things to higher powers here. They're not so important. They're not so important. The most important one is phi to the fourth and expanding the potential in a power series. You can put in more, but this is the most important thing. And in fact, it's also traditional to put a 4 over here. You'll see why in a moment. A 2 over here and a 4 over here. What is this number? This number is called a quartic coupling constant. Quartic because it has phi to the fourth. It is dimensionless. It's a pure number. Right? We think we know something about that pure number, not from direct experimental evidence, but from a lot of indirect evidence. And what we know about that number from somewhat indirect properties of weak interactions is that it's small, but not absurdly small. Probably about 1%, probably about 1.01 or something like that. Compared to the numbers we're going to be thinking about later, this is a number which is of order of magnitude 1. It's not 10 to the minus 20, it's not 10 to the minus 15 or anything like that. So just think of it as a number for the moment of order 1. It's also dimensionless. Mu is not dimensionless. It has units of a mass. Okay, now let's try to find out what F is. F is the position at the minimum here. All we have to do is minimize this with respect to phi. We cooked it up so that it would have a minimum, a rapidly falling quadratic term, and then taken over by, incidentally, near the origin, this is smaller than this, right? Phi to the fourth is smaller than phi squared near the origin. So this has not got much effect near the origin. It picks up steam and eventually becomes much bigger than phi squared when you go to large phi. So that turns it back up. That's the logic. Okay, let's just find the minimum of phi, the minimum of V with respect to phi, and that will tell us how much the field gets shifted. All right, that's easy. We just differentiate with respect to phi. The derivative of phi squared is 2 phi. That eats up this 2 down here. That's why I put the 2 down there. Minus mu squared phi. This is the derivative of V with respect to phi, plus lambda, which is a number of order of magnitude 1, phi cubed. I also put the 4 down here, so it would kill the 4 when I differentiated with respect to phi to the fourth. And we set that equal to 0. All right, now we can divide by phi. We divide by phi, make this phi squared. And what do we get? We get phi squared is equal to mu squared over lambda. Again, lambda is an ordinary number. Don't think of it as very big or very small. This is the value of phi at the minimum. It's also called F. It's also the shift of the field, F. And so F squared becomes mu squared over lambda. Again, I emphasize, lambda is not the interesting number here. It's a common garden variety number like a 1 or a 10th or a 100th or something like that. It's not very big, that's for sure. Okay. F is controlled by mu. F is also approximately the mass of the Z and the boson, the Z and the W boson. It's also the thing which comes into the mass of the fermions. Where are they? All of the particles have masses proportional to F. Let's take the square root of this. So it's mu, or F, or mu, which is the controlling factor which controls all of these masses. All of them. All the masses of all the particles that we know about. Okay, that raises an interesting question. Why are all of the particles that we know about controlled by the same phenomenon, namely F? Why aren't there particles which have masses without spontaneous symmetry breaking? We can certainly make up a theory of such particles. For example, just make up a particle whose left-handed and right-handed components both have weak charge. Then we have no reason to put this phi in there. We wouldn't put the phi in there. And you could put any mass that you like in front of it, and it's perfectly symmetric. So if there was a particle whose left and right-handed components both interacted with the weak interactions the same way, they could have a mass which was not proportional to F. All kinds of other particles particles that don't have any weak interactions at all, if there were such particles, could have masses which are not controlled by F. The general thinking, which we'll come to, and I'll explain why this is the general thinking, is that the natural mass scale for particle physics is enormous. Much, much higher than the masses of any of the ordinary elementary particles. It's thought that only this one number F is the unusual number in physics, the very, very small mass scale, whose origins are at present unknown, but what is thought, and I'll explain as this quarter, next quarter, various points, the idea that really the only parameter, the only small mass parameter in nature is this F here. And those particles, which by necessity have to have masses proportional to F, why? Because it's in the nature of their mathematics that they would have to be massless if there was no shift of F. Only those particles are light enough to have been detected at present. That's the belief. That's a very widespread belief that there's a good reason why all the particles have masses proportional to F, because any that don't probably have masses which are much, much larger. But still we have to explain the smallness of F. Small compared to what? Well, that's an interesting question. Small compared with what? What is the natural mass scale for elementary particle physics? So that's where I think we want to go next. Hmm? That's one possible mass, yes. Yes. All right, let's see. I think we'll take a break in 2 minutes, but yes, one possible mass, which we'll talk about in a few minutes after the break, is the Planck mass. Another is the so-called unification mass, which I'll show you what it is. These masses are typically 16 or 17 orders of magnitude. Well, let me see. 15 orders of magnitude heavier than the mass than F. 15 orders of magnitude heavier than the Z or W boson, for example. Right? So what we're left with then is a puzzle. Why is this F quantity so small? Once we can understand why the F quantity is so small, it drags down the masses of all the other particles. It drags them down simply because they cannot have mass other than proportional to F. They would naturally be massless in a world without spontaneous symmetry breaking. So, yeah.
Would you say that again about the 15 orders of magnitude?
Yeah, the natural, all right, F is a number of about 100 GeV. All right, that sounds like that sounds like a big mass, all right? The other mass scales which come into particle physics, which we know about, the other possibly much more fundamental mass scales are much, much heavier than that. 15 orders of magnitude heavier than that.
And what particles correspond to that?
None that we've ever discovered, obviously.
Yeah, right, any but we predicted?
Yeah, well, yes, of course, particles we predicted, but why did we predict them 15 orders of magnitude higher? In other words, when I say that there are other mass scales that we know about them from something. So the question is, where do we know about them if we've never seen them, if we've never seen particles of those masses? And we'll talk about that after the break. Yeah.
I gather that in these very, very low temperature condensed matter, Bose-Einstein kinds of things, there's all sorts of analogs to particle physics and whatnot.
Right.
But aside from that, is there any common in solid state physics or any common example of a Higgs-like mechanism?
Yes. Yes. All right. So you asked about Bose condensates. So a Bose condensation, or more precisely superfluidity, which is similar to a Bose condensation, it's a condensation of helium atoms. Okay. Helium atoms, of course, not elementary particles. Okay. But on some scale, they are elementary particles. If you're interested in scales of order molecular size, a helium nucleus is an elementary particle, and it can be described by a field. Okay? That field naturally in an ordinary vacuum has a value 0, just corresponding to no helium atoms present. Okay? Spontaneous symmetry breaking can happen, which can shift the value of the helium field. When that happens, in the same way that F is a shift of the Higgs field, when that happens, it's roughly speaking called a Bose condensation. When the Bose condensation happens, it spontaneously breaks a certain symmetry, and it's called, and it creates superfluidity. But if the helium atom were charged, if the helium, not the helium nucleus, the helium atom, if the helium atom were charged, it would behave like the Higgs boson and make a mass for the photon. Now, does that ever happen? Anything like it ever happen? Yes, it does. In a superconductor, electrons can pair up and bind together in the superconductor, very weakly bound pairs, and those pairs of electrons have charge 2. Right? They're not helium atoms, they're not neutral helium atoms, they're called Cooper pairs. And they're bound configurations of electron, not electron and positron, but electron and electron.
Are they separated? The Cooper pairs, aren't they separated?
They're separated, they're not very far separated in space. They're separated at the opposite ends of the Fermi surface. Right. No, think of them as particles. First approximation, think of them as particles. They're charged particles, and then they condense. They condense, which means the field for this pair of particles gets shifted. You can think of that field as really just being the product of the electron field with itself, describing 2 electrons, or you can think of it as a new object which carries charge 2. When that field gets shifted, it creates a condensate of Cooper pairs. It creates a kind of superfluidity for the Cooper pairs, but it's now a superfluid of charged particles. It becomes the Higgs phenomena. It's, of course, a superconductor. And the superconductor, in essentially every possible way, behaves like the Higgs phenomenon. The photon gets mass. Now, it's a tiny, tiny mass because the scales are so terribly different. But the Compton wavelength of the photon becomes finite, and it behaves very, very much like this spontaneously shifted Higgs field. In fact, the phenomenon was first discovered in the context of superconductors, and was rediscovered entirely independently by Higgs and other people. Okay, let's take a little break. When you begin at the primordial description of elementary particles, you begin with a Lagrangian, and in the Lagrangian there are a collection of parameters such as masses of particles, charges of particles, and they're sort of the input. On the other hand, they're very rarely, if ever, the actual measured quantities. The measured quantities that you actually measure are usually the product of all kinds of interactions and things that take place between the high-frequency modes of a system and the low-frequency modes of the system, which renormalize or change the values of the parameters that you associate with experimental observations. An example is electric charge. So let's talk about that a little bit and how charge gets renormalized. I'm not going to do any calculations. Calculations, you'll have to go and get a book and try to follow it. But the phenomena is a fairly simple one that's well known. It occurs in condensed matter physics. In fact, it just occurs in classical electricity and magnetism associated with electric, what's it called? Dielectric, thank you, with dielectric materials and conductors. The actual observable charge, normally observed charge of an object, is defined by the Coulomb law. But the Coulomb law at large separation, the asymptotic force between two charges when they're far apart, and that force, as you well know, is the product of the charges. Let's call it E1, E2. Let's take them to be equal charges. And in particular, let's suppose they have charge of the electron, just to be simple. Then it's just E squared divided by R squared, or in the potential energy, just E squared divided by R. All right, so you take two charges far apart and you measure the charge, you measure the force between them. At any given distance, it will not be precisely given by this formula, but if you asymptotically separate them, then you'll find asymptotically with respect to R, the force between them, or the potential energy between them, goes like E squared over R. Attractive for opposite charges, repulsive for like charges. And that defines, if you like, the charge of a particle. Coulomb law at spatially very large separations. Now, if in a material you do this, you take charges in a material, or even just the air, and you separate them and see what the force law is, you'll find that it's not exactly given by the formula in which you go to the particle physics table, the particle physics table of particle properties, read off the electric charge of the system. Typically, you won't read off the electric charge of an ordinary chunk of material, but you might happen to know how many electrons or how many excess protons or electrons are in it. So you might know its charge in units of the charge of the electron. You take them apart, and you discover, no, the force is always a little bit less than that, always a little bit less than that, unless you're in absolute vacuum. An absolute vacuum, completely empty space, by definition, the electric charge is what you measure by measuring the force at a large distance. Now, what is it that happens in a material? Let's begin with a conductor. With an electric conductor, what happens to a charge that's put into the conductor? Well, the charge creates some electric field. For example, suppose it's a plus charge. It creates an outward electric field. The electric field creates a current. The current starts charges moving. And until the charge is completely discharged, until it's completely discharged, in other words, until the charge has gone out to the boundary of the conductor, the flow of charge doesn't stop. Okay, so the charge flows until the charged object, let's draw the charged object over here. Here it is. Charge flows away from it, collects on the boundary, but let's put the boundary off on Alpha Centauri someplace. And of course, an opposite charge, so if this is plus, an opposite charge cloud is found around it that completely discharges it so that outside there's no electric field at all and no more reason for the charges to flow. Now, these charges are, of course, bound to the charge, to the positive charge. They're bound to it, and the whole thing forms a neutral structure. If you take another negative charge over here, exactly the opposite thing will happen to it. It will create some plus charge around it. Same deal. The charges will flow until it's completely neutralized. And now you take these two charges. You thought you had two charges to begin with. You evaluate or measure the force between them at large distances, and you find out that there is none. Okay? So the charge that you put in to begin with is not the experimental charge at the end of the day. The experimental charge at the end of the day in this case is just plain 0. Okay. Now what happens as you start moving the two charges, let's suppose they're really small, and you start moving them closer and closer together.
Is this screening?
Screening.
Okay.
Yeah. This is device screening. Okay. Supposing these charges are really small, in particular they're smaller than the clouds around them that form. The clouds around them are controlled by various properties of the metal and so forth, and the electrons moving in the metal. And we imagine making these charges even smaller. We bring them really close together. We bring them so close together that the screening cloud can't get between them. Typically, there's a scale for the screening cloud. It's controlled by the dynamics of the electrons in the system. And the screening cloud, the particles making up the screening cloud typically have a certain distance between them, and that distance controls the size of the screening cloud. When you bring these two particles closer than the screening cloud, they're no longer screened. They actually feel each other's raw basic charge, and you see that there's a Coulomb force between them, which is the usual E squared over R. Okay. So you could say then that the charge of the electron, or the charge of the particle in this case, is really a function of distance. In the case of the conductor, E of R is 0 at very large r. It's whatever the ordinary charge of the particle is at very small r, and the force law, instead of being just plain E squared over r, has E squared of r divided by r. This is just a definition of E squared of r, if you like. I don't put anything new into it by calling it E squared of r, but it does have a nice sound to it. It's called the running charge. Running is a function of distance between them. Okay, now what happens if you have something less extreme than a conductor? For example, a dielectric. A dielectric, if you like, has electrons which are bound to the atoms. Electrons are bound to the atoms, but they're free to shift a little bit. If you like, you can almost think of the electrons as being on springs, where the one end of the spring the electron is attached to, the other end of the spring the ion, the positively charged ion, is attached. And ordinarily, the electron moves symmetrically, vibrates symmetrically. Of course, this is not really a good picture of an atom, but it's good enough for our purposes. The electron oscillates and vibrates back and forth symmetrically about the atom. So on the average, the dipole moment of the atom is 0. But now you put the atom into an electric field, and what happens is the electron cloud shifts a little bit. Right? It shifts a little bit, leaving a dipole left over. Current doesn't flow. Charge just shifts a little bit because they're bound to the atoms. Okay, so now what happens if you put a charge into a dielectric? Well, a very similar phenomenon happens. Let's suppose we put a minus charge in over here. All the ions are, they're heavy. They don't move very much. But the electrons, which are bound to them by the springs, move out away from the central atom. What does that leave? That leaves a little bit of plus charge here. But it doesn't completely screen the charge. It screens some fraction of the charge. So that if you look very, very far away from the charged particle, you'll find that the field, the electric field, is diminished by a certain fraction, but it doesn't go to zero very far away. Okay? The fraction is controlled by the dielectric constant. The dielectric constant will tell you what the screening is. So again, you'll find that a large separation, this plus charge and this minus charge, don't satisfy the expected Coulomb law that you might have expected from the actual, let's call it the bare charge of these particles, but it's diminished by this effect. It's diminished. The Coulomb law is correct, but with a diminished value of the charge. So in this case, you would also have an E squared of R or an E of R. Again, if you bring the charges very close together so that they're within the screening cloud, then you feel the full strength of the bare charge. So again, E squared is a function of R. In this case, it wouldn't go to zero in infinity. It would just go to some constant fraction of the original charge. Again, the concept of a running charge. All right, now, exactly this phenomenon, it really is exactly this phenomenon, happens in quantum field theory. And the origin of it is the pairs. Let's take quantum electrodynamics. In quantum electrodynamics, the vacuum is full of electron-positron pairs. Okay? There are Fineman diagrams where electrons, positrons are created by photons, even just electron-positron loops with no photons, and they inhabit the vacuum, if you like. The other way you can think about it is you can think about it in terms of Dirac's negative energy C. The vacuum is filled with this negative energy C. Or you can imagine that there are electron-positron pairs in the vacuum. What happens when an electric field comes along? The electric field will shift the positrons one way and shift the electrons the other way, so that every little virtual pair, electron-positron pair, will become polarized. Polarized in exactly the same way that atoms become polarized by an electric field. The plus charge is shifting one way, the minus charge is shifting the other way. That's what happens in the vacuum when you put an electric field on. Okay, that's step number one. Step number two, of course, you put in what you thought was an original bare charge of magnitude E. The charges in the vacuum rearrange a little bit. The vacuum is basically a dielectric. It's basically a dielectric. The charges shift a little bit, and in such a way that negative charges are screened by a little bit of positive charge from these virtual pairs, and positive charges are screened by a little bit of negative charge. The upshot is the charge that's felt at a large distance is not the same as the numerical value of the charge that you put into the Lagrangian, which is usually called the bare electric charge. But again, you start moving the electrons closer and closer to each other, and at some point they get closer than the size of the screening cloud. But there's one difference in this case. In this case, there is no set distance that the electron-positrons tend to be separated by. The right statement is that the separation between the electron-positron pairs depends on their energy. The higher the energy of the virtual pair, the closer they will be. So there will be electron-positron pairs which form relatively big, let's call them atoms. They're not atoms, but let's call them atomic neutral systems. There will be ones of higher virtual energy which are smaller, ones of yet higher virtual energy which are even smaller, ones which are higher energy which are even smaller. Okay, so what happens when you put the charge in? and bring another charge closer and closer and closer. At first, you will bring them close enough that they'll be within the distance of the low energy virtual pairs. The low energy virtual pairs will no longer be able to screen the charge, and so the charge will look a little bit bigger than it would when they were far apart. Why? When they were far apart, they were completely screened, not completely screened, but they were screened by all possible virtual pairs. You bring them a little bit closer, the low energy virtual pairs, which had a large separation between them, you bring the charges closer than that, and the low energy virtual pairs are no longer important in screening. But the higher energy virtual pairs are still doing some screening. You bring them a little closer, the higher energy pairs fall out of the equation because they're too far apart, and yet higher energy ones are still there. The effect is that E squared of R is a function which keeps changing and changing and changing with R. It doesn't stop changing at some particular small distance. The closer and closer you bring the electron together, the larger the charge will appear to be. So if you were to plot, by virtue of the fact that there are pairs of every possible energy in the vacuum, so if you were to plot the electric charge as a function of radial separation, let's plot it as a function of inverse radial separation. Inverse radial separation is like energy. The closer things are together, the higher their energy. So let's plot it as a function of inverse separation, 1 over r, which is also related to energy or momentum or whatever. Then the electric charge that you'll see will increase. It'll increase very slowly, in fact. It's a very slow logarithmic increase. It doesn't increase rapidly. That's why it's very hard to see in an experiment. It's a logarithmic gradual increase of the size of an electric charge as you study smaller and smaller distance phenomenon. It's also true, for example, electric charge comes into calculations of scattering of electrons. If you scatter electrons at a low energy, they only get within a certain distance of each other. The higher the energy you scatter them, the closer those electrons can get to each other by virtue of the uncertainty principle. And when you do the calculation, you have to put in the running charge. If you scatter electrons at enormously high energy, they behave as if they had a larger charge than at smaller distances. So that brings us to the idea of running charge. All right? What is the fundamental charge? What is the most fundamental value of the charge? Is it the one at long distances? No, that's the one that's controlled by all of this complicated screening taking place. As you get to smaller and smaller distances, you sort of peel away the screening cloud. As you get to smaller and smaller distances, you peel away more and more of the screening cloud. So it's really at the smallest distances where the basic parameter that you put into the Lagrangian, the bare charge, manifests itself. Okay. Yeah?
How small is small where you start seeing a significant effect?
Well, you start seeing a measurable effect, but a high precision measurable effect at a few times, at about the Compton wavelength of the electron. So what's that, 10 to the minus 11th Compton wavelength of the electron. The electron is half an MeV, so that's about 10 to the minus 11th centimeters. About 10 to the minus 11th centimeters, you start to see the running of the charge. Not below that.
But this thing continues, it doesn't live long.
Well, it would keep going on if the physics didn't change somehow at very small distances. We don't know what the physics is at very, very small
Well, I
distances.
mean, you just said something about sort of implying that the small one was there. There we don't know what happens, actually.
At very small distances. Right, that's right. That's right. We don't know what happens at very small, so we can only extrapolate a certain, yeah. Yeah.
So for gluons, it's kind of the opposite thing. There's some anti-screening.
It does. It does. Well, that's a more complicated phenomenon. A more complicated phenomenon that's closely connected with the fact that gluons interact with gluons. And because gluons interact with gluons in a very nonlinear kind of way, the effect is actually the opposite. Right? This is. You go to infinitely small distances and you measure at infinitely small distances the interaction, and that's the bare electric charge. But you'll never get to infinitely small distances because. No, it doesn't asymptotically. It just keeps growing and growing and growing.
Yeah, a logarithmic function is unbounded.
Right. Right. So it keeps growing until something happens that was not taken into account by these calculations. What could it be? A smallest distance in the world, the Planck distance, something else happens, and from experimental physics, we don't know what terminates this. We certainly believe it's terminated at the Planck length. This physics certainly doesn't make sense at Planck length.
But there has to be a particular length we say that's bare electric charge.
So let's call it Planck length, to be specific.
Okay.
But you see, you can compensate. You can change that length. And if you also at the same time change what you called the bare charge, it would compensate. Right? So at any given level, you could terminate it, call that charge the bare charge at that length, or change the length scale. If you appropriately and judiciously change the value of the bare charge, what comes out at the low energy end won't know about it. All right? So that's the phenomena of renormalization, changing things in such a way as to keep the physics, the experimentally known physics, fixed.
Is that what you're zooming in and attenuate? Is that
You're zooming in and looking at closer and closer distances. Now, of course, we don't do that experimentally, so we do that in our mind, and we ask, how do we have to change the physics at smaller and smaller distances to keep it fixed at experimentally accessible distances? How do we have to change the electric charge as we go to smaller and smaller distances in order to keep the physics fixed at any given wavelength? So what this is telling us is that as we go to smaller and smaller, more and more refined description, more and more fine-grained description, the value of the electric charge that we have to put into the bare description has to grow. Now, as I said, that will change at some point where the physics of quantum electrodynamics gives way to something else. Okay, so that's the electric charge. Yeah.
Does the same phenomena happen with gravity? The equations are somewhat similar.
We'll talk about it's quite a different phenomenon, but we'll come to it perhaps today. I don't know if we'll come to it today, maybe. Okay, now let's talk about the strong interactions. The strong interactions, things are more complicated. Let me remind you of what we learned about the force law between quarks. The force law between quarks does not behave like E squared over R. What happens is some new phenomena where the flux lines that come out of quarks, these are not the electromagnetic flux lines. These are the flux lines of QCD. They're called chromoelectric flux lines, attract each other. They attract each other in a way that does not happen in electrodynamics. It's the self-interaction between gluons. All right? And that has the effect of turning the Coulomb field into long tube-like structures, which are sort of squeezed by the vacuum into these long tube-like structures. The effect of this is as you separate quarks, the energy grows linearly with the separation between them. You create this Turkish Taffy Gooey Stuff in between them, and the energy of it grows simply as the length of the gooey thing between them. That means that the force law, the energy grows linearly. What is the force? All right, so let's write that down. Instead of the energy growing like E squared over R, it just grows linearly with R. So this is the wrong formula. We should have put here perhaps E squared or something like E squared times R. Let's not call it something times R. Well, we can either say we had completely the wrong theory, or we can say that E squared is growing like R squared. We can say the picture from electrodynamics, the charges are screened. Simply the opposite happens, that E squared grows with separation. Something happens in this nonlinear effect here, which is quite the opposite. And so E squared grows with separation. Incidentally, at very small distances, again, distances which are so small, smaller than the size of these flux tubes, it reverts back to E squared over R. Okay, so it reverts back to the good old Coulomb law. But another way of saying it is that instead of E squared as a function of distance getting larger with distance, it actually gets smaller with distance. E squared is getting smaller. No, sorry. With inverse distance. It's getting smaller with inverse distance. Larger with distance, smaller with inverse distance. So therefore, if I plot the quantum chromodynamics coupling constant, it will fall as a function of inverse R, like that. What about the one for the weak interactions? Well, the weak interactions are sort of in between. They're sort of in between. They have similarities with both. They're in between. So they go like that. Well, maybe not as fast. It's an interesting and quite remarkable fact that if you actually take the standard model and you work out how the charges, first of all, you need to know what the various coupling constants are in the laboratory. Those are the ones that control physics at whatever scales you've done your experiment, 100 GeV or whatever, and you put in their values. And then you run them using just the standard model, the polarization of the vacuum and all the properties from the standard model. These three numbers more or less come together at a common point. Right? They more or less come together at a common point. Now, in a more refined, well, in the supersymmetric version of the theory, which we will talk about next time a little bit, next quarter, they come together with rather high precision, about 1%. About 1%. Okay? They come together about 1%. That looks like there's something happening at some energy which is unifying these forces. Their coupling constants seem to be the same at some high energy here. If you just extrapolate these curves, the curves are calculable. Of course, you have to assume that no new physics comes in. That no new physics comes in, or if new physics comes in, you have to take it into account. New physics might shift these curves a little bit. In the supersymmetric version of the theory, these three numbers come together very nicely to about 1% at an energy of about 10 to the 16th GeV. Why is that energy so high? It's because these curves vary logarithmically. They vary slowly. Okay? When things vary slowly, they vary slowly. And so it takes a long range of scales before they come together. And they come together at about 10 to the 16th GeV, 10 to the 14th times larger than the mass of the W. All right, so it's some huge energy. It looks from these curves that some kind of unification is taking place there. Now, is this good enough to, a relatively high precision agreement in the supersymmetric theory. In the non-supersymmetric theory, it's not such high precision agreement, but it's tantalizing and it's interesting that this is the tendency for things. All right, if this is correct, you might guess that the fundamental length scale of particle physics of the standard model is up at this 10 to the 15 GeV. It's where the input seems to be simplest. Simplest in that the three coupling constants seem to be the same. We'll talk about what that means mathematically. It has a very deep could have a very deep mathematical meaning. But for the moment, it's just an observation about numbers, that they come together at a particular energy. Now, that energy also happens to be the place, if you were to plot the strength of gravitational forces. Gravitational forces are very weak at large distances, but I'm going to show you why in a moment. They get stronger and stronger and stronger at small distances, not only because of the usual 1 over r squared in the force, but above and beyond that, the forces of gravitation become stronger and stronger. And if you were to lay on top of that, let's see, the forces of gravitation would become strong at small distances. So that would mean gravitational forces, which are incredibly weak at long distances, would do something like that. And they don't quite all cross at the same place, but they cross within a factor. You remember, these are logarithmic curves. They cross within a couple of orders of magnitude of each other. The gravitational, the weak, the electromagnetic, and the strong interaction cross all within a couple of decades of energy of each other, or a couple of decades of length scale, at about somewhere between 10 to the 16th, 17th, 18th GeV. So what all this means, especially the gravitational side of it, we don't know. But if there is a unification scale, and if this really does correspond to some unity between the three forces, it looks like it happens at a scale which is not too different than the Planck scale. The Planck scale is the scale where gravity would become comparable to the other forces. So let's talk a little bit about gravitational forces and why I say that gravity gets stronger at small distances. Ordinarily, now we're going to talk about what happens to gravitational forces as you vary the distance scale. And the only point here is that when you understand how gravity depends on length scale, you'll find out that gravity sort of falls on the same ballpark with the other forces at scales which are very small. That gravity is really no weaker than these other forces. Okay, so to understand this, we first have to erase the blackboard a little bit. We're used to thinking that, that the force law of gravity is 1 over r squared, or Coulomb. Be surprised if I told you it's really 1 over r cubed at very small distances? You wouldn't be surprised. But you wouldn't.
I thought I heard something like that.
Okay, so let's go through why it's 1 over r cubed at very small distances. The reason is we write down, what do we write down? We write force. Let's work with force this time. We worked with energy before. It doesn't matter which we work with. Force is equal to m, two particles, masses, r squared, and Newton's constant, right? That's the force between two particles. All right, now this is a non-relativistic formula. This is the formula for particles at rest. When particles have a high energy, or when objects have a high energy, it's energy that gravitates and not mass, not rest mass. A moving object will gravitate more than an object at rest. If you take a box full of high-energy particles, those high-energy particles will gravitate more than they would if they were brought to rest within the box. So the right formula, or a more correct formula, is to put here, use E equals mc squared, or not m squared, E equals mc squared, or better yet, m equals E over c squared, and put in here energy of particles, E over c fourth, I believe, right? Over c fourth, all right? So this is a formula which is more accurate when the particles are relativistic. Okay, now let's go to quantum mechanics and imagine bringing two particles very close together, much closer together than their Compton wavelengths. Because of the uncertainty principle, if we've brought them close together and we know that they're close together, that means that their momentum is extremely uncertain. To say that the momentum is extremely uncertain, you can say that the momentum is very large. Roughly speaking, if you brought them to within a distance r of each other, the momentum of them must be at least of order, what is it? H bar over r, right? Okay? Now, what about the energy of these particles? The energy of these particles, you might think, well, the energy of a particle at rest is mc squared. Right? If it has a little bit of velocity, you add plus 1/2 mv squared. Sorry, 1 mv squared over 2. But what happens when the momentum gets really large when r gets very small? When r gets very small, these particles become highly relativistic. Why? Their momentum gets much larger than any pre-assigned number when they get very, very close together. What's the energy of a particle, a relativistic particle, with momentum p? Relativistic means it's moving with almost the speed of light. Anybody remember? What is it? No, that's non-relativistic completely. No. The energy is p times the speed of light. Right. P times the speed of light. Okay, so we can now say p is h bar over r. And now we can plug this into the force between particles. Okay, so what is it? F is equal to h bar squared. Let's just, the particles come close together. Let's assume they both have about the same energy, which is a good assumption. So that's h bar squared, c squared, over r squared. That's just e squared here, e1 times e2. That's this factor here. Then there's a c to the fourth in the denominator. From here, there's a g and another r squared. So r to the fourth. Did I get it right? Right. The c squares cancel. Yeah. Well, they don't cancel. C squared. All right, when I said the force law was 1 over r cubed, I meant the energy, not the force. The force is 1 over r to the fourth. Okay. So when you bring particles really close together, squeeze them by whatever means. Either an accelerator accelerates them to very high energy so they can get very, very close together, or you put them in a box and squeeze. Well, there's no box is going to hold particles that are that relativistic. But somehow or another, when the particles get that close together, the force law is quite different than Coulomb. It's 1 over r to the fourth. Okay, now let's ask the following question. Yeah.
Here, so it's an attractive force.
It's an attractive force, right. And it is much more potent at small distances than it is at large distances. 1 over r to the 4th is much, much bigger than 1 over r, than 1 over r,
This is
1 over r squared.
This is because the relativistic speed up causes the mass to increase, but not the charge to increase.
Right,
So that-
right, exactly so. Exactly so. Okay, now let's ask, at what length scale r is the gravitational force approximately the same order of magnitude as the electromagnetic force? Let's do a little, there's the electric charge, the electron's electric charge is a pure number. It happens to be fairly small. Let's forget it, but not ridiculously small. It's a fairly small number of something like 1/10 or something like that in natural units. So for the first round, we could just set the electric charge of an electron equal to 1 for simplicity. And then we could ask, at what length scale is the force, the gravitational force between a pair of particles the same as the electromagnetic force? Let's say a pair of electrons. Does that ever happen? At ordinary scales, electric forces are vastly larger than gravitational forces, electric forces. As you bring them closer together, because the gravitational forces increase like 1 over r to the 4th, eventually the gravitational force will cross the electrostatic force, and at smaller distances will become even more important, even larger. So let's see where that happens. To find out where that happens, we should set this equal to E squared over R squared. For simplicity for the moment, let's just set the electric charge equal to 1. It's not equal to 1, it's about 1/10 or something, it's smaller than 1.
G or E? G or E?
G or E?
You just erased G.
Oh, sorry, I didn't mean to erase G. How do I do that? E. Let's simplify and put a 1 here, which is not too wrong. E squared is really something like about 1/10, okay? But it's not too bad. It's approximately right. Now we can read off from this at what scale these two kinds of forces become equal to each other. Just multiply by r to the 4th. This becomes r squared here. Now take the square root of it. Wait, did I... something wrong.
You had r 4th?
Yeah.
It'd be r squared now.
It's r squared, yeah.
Okay.
I think I made a mistake. I still think I made a mistake. No, but it's not right. Wait. Yeah, I know the answer. H bar c over c squared r to the 4th is 1 over r squared, right? So I have h bar g over c. H bar g over c is equal to r.
It's r squared, not r to the 4th.
There was an r to the 4th here, right? And then there was a 1 over r squared here. So I got an r squared here, right?
I think you're doing r, right? If you're taking the square root of both sides. What you read out sounded like you're just taking the square root on both sides.
What am I going to get? I'm going to get h bar over c,
Square root of g.
h bar over c squared of g, right?
Yeah. Equal to r.
R. Which is the square root of h bar squared g over c squared. No, c squared. Is that dimensionally correct? Must be.
Well, you took out electric charge.
No, electric charge is dimensionless. And wait a second. Yeah. Hold on. I think I lost some dimensions. This is energy. All right, let's do it in terms of energy. It's r cubed in terms of energy. And I want to set that equal to E squared over r. But this is not dimensionally consistent if r is dimensionless. So I need some h bars and c's in there. Well, I want the charge to be dimensionless because I happen to know its value in dimensionless units. It's about a tenth. It's close to 1. So we have to put some correct. This has units of energy, right? So we have 1 over r, and if I put an, this is not correct yet. It's not correct. It's not dimensionally consistent. If I put an h bar here, then this would be momentum. If I put a c there, it is now dimensionally consistent. All right? C h bar over r has units of energy, and now this electric charge here is dimensionless, and that's the one which is about a tenth, close to 1. Okay, so I made a mistake. I thought I made a mistake. I should have, uh-oh, I erased it. It's lost, it's gone.
That's okay, right. H squared P.
I think it's right now.
Yes.
Okay, now multiply it by r cubed, and we get r squared up here. Now we get a c cubed down here, and remove an h bar. And I get r now is equal to the square root of g h bar over c cubed. I think I like that better. All right, what is that length? That's the Planck length. That's the Planck length. So the Planck length is the place where, because of this growth of energy with squeezing, with diminishing the wavelength, because of that, the gravitational force increases and becomes comparable or even bigger, a few factors of 10 bigger than the electromagnetic force at the Planck length. So they also, so the electromagnetic force, the weak force, the strong force, and the gravitational force all grow or all become more or less comparable somewhere near the Planck scale. This is thought to be deep. This is thought to be something important. If it is as important as it sounds, then the puzzle becomes not why is the Planck length so small, or why is the Planck mass so large, or why is that 10 to the 19th such a big number. It is why that f is so small in natural units. How does it happen that that f, which controls the masses and the energy scales of all weak electromagnetic, all the ordinary interactions, in particular, controls the mass of the Z, the W, the quarks, the electron. Why is it so small? That's one number, which is some 15 orders of magnitude smaller than any fundamental length scale, as far as we can tell. And it's just that one number which is very small. Once that one number is explained, why it is so small, all the masses of all the elementary particles that we know about follow. All the others, for all we know, could be up at the Planck mass, at the natural scale. They have no reason to be light. Their masses did not have to be proportional to this symmetry breaking scale. So that's kind of where we are, puzzled about why this f is so small. Now, we'll go more deeply into this next quarter. It's not only that it's small, it's also very, very finely tuned. And we'll come back to it.
So if you could somehow calculate f, then you could calculate the other masses. Yeah.
If you could calculate f, you could, but any ordinary calculation of f will give a huge number. Why? Because it'll come out to be proportional to the fundamental scale, unless there's some incredible conspiracy that, so, yeah, you can calculate it in all sorts of theories and it'll come out huge.
I'm trying to visualize the Planck length in terms of the screening distance when we get so
In
close.
gravitational physics, it's not helpful to think of it as screening.
Okay. Yeah, that's right. That's
You know,
right.
it's just not useful to think of it as screening.
If you had higher orders of phi,
Higher orders in what?
of the Higgs field, phi, and say phi to the sixth, etc.
P.
Each of those
P. What's P?
P.
P. 5. Yeah, P 5. P 5 full power.
Each of those appear in a Lagrangian.
Well, there are real reasons why not. You wouldn't want to put in 5/5 there because that would break the symmetry between plus phi and minus phi. You could put 5/6 there, but there are.
Those are annihilation and creation operators, those phis.
Yeah.
So that represents 4 Higgs particles coming together.
Absolutely. Okay, so that's another, right. Once you know these numbers, you can predict something about the scattering of Higgs bosons. 2 Higgs bosons go to 2 Higgs bosons. Right.
Is Lagrangian a polynomial in all the field variables then? Oh, okay, so that's pretty restrictive.
Well, it's not. It's more restrictive than you think. Beyond phi to the 4th becomes what is called non-renormalizable, which is a bad thing to have in a theory. So we can talk about why phi 4th is the natural endpoint of this.
The Lagrangian is a polynomial in all the field values, and there's never any exponent above 4.
Right. Except when there is.
Have we left out any terms like self-interaction or?
Well, self-interactions are what goes into the running of these coupling constants. For example, the self-interactions between gluons are what gave you the opposite effect from what happens in electrodynamics. Self-interaction between flux lines pulls them together into a sort of cable, and the upshot is that the running electric charge changes quite differently.
And the other thing I thought of was cross terms between kinds of interactions.
Well, there are such things. They come in higher orders, and you have to calculate them. But fortunately for us, all of the coupling constants are quite small, so the higher order cross terms are smaller than the things that they're perturbing.
What exactly did you mean when you said F is finely tuned?
I didn't come to it. We'll discuss it. I'll tell you, not now, but yes, it's important.
Since we've talked about renormalization in groups, can you say something about what the renormalization group is?
Not tonight, but at some point. Okay.
For more, please visit us at stanford.edu.